Okay, so good morning, everybody. Nice to see everybody. Thanks for coming out on a Saturday. Also, I think it's the marathon this week, so thanks for coming out. And I lived in Boston for a long time, so I know on marathon weekends it's usually beer time. So thanks for coming. For people who weren't here last time, my name is Anthony. I'm a research scientist in the Enrico Fermi Institute, and we're talking about understanding the building blocks of nature with particle collisions and AI. And so just a reminder of what our plans are. So, okay, cool. Last time we did some introduction to the lectures, and then we have a roadmap for 8 lectures where we're going to talk about big physics questions, experimental considerations, and then go into more details of how AI is being used on the ground. And today I wanted to spend more time talking about just the big physics questions that then will motivate the third lecture, which is translating them into experiment, and then the 4th, 5th, 6th, 7th, and 8th, which is actually details from on the ground. And the thing I actually wanted to start off with, I know for me when I listen to lectures, it's really nice to have a refresher on what happened last time. So I'm going to spend maybe 5 or 10 minutes just going through a refresher from before. And the thing I want to start with is flashing again my favorite plot in physics. So this is the formation of the universe, the history of the universe as a function of time. And I apologize, I tried to make the text bigger, but on this one I couldn't do a good job at it. And this is an evolution from the Big Bang to inflation, and then different scales of the universe versus temperature and versus time. And previous lecture series, we had talked a lot about large-scale structures, so taking pictures of the sky with really high-resolution cameras and telescopes, and understanding formations of galaxies, dark matter clustering, all sorts of exciting things. And then this lecture series, we're talking about the small-scale behaviors, so particle physics, the most indivisible pieces of matter, and how they interact with each other. And the motivation for that is to understand, A, the building blocks of nature, and second, to see how those small interactions leave an imprint on the universe. And as the universe expands, you get large-scale behavior that are dominated by these imprints. And so then what we talked about is we gave a small intro to what this theory that we're talking about is, the so-called standard model. And like I said, we're talking about indivisible pieces of matter. So we're talking about fundamental particles and how they interact via forces. And so this is a diagram that we'll come back to later when we talk about big physics questions. So here we have the 17 particles that we know about, the quarks. So for example, the up and down quark that make up the proton, the leptons, like for example, the familiar electron. And then we have the particles that mediate forces. So like the photon that mediates the electromagnetic force, the gluon, which is what binds together protons, so binds together these quarks. Then we have the W and the Z boson that mediates the nuclear decays. And then we have the Higgs boson that ties everything together, which we'll talk about a bit more later. And this theory is a general theory where we take experimental input, so we measure things at colliders and various other places, and we tune the theory, and then we compare with predictions. And so like I said, a big theme of this lecture series is learning by doing collisions. And so what we're doing is we're studying the particles and the forces, and how we're doing that is we're creating the conditions here on Earth to actually see interactions between them. So this is notably distinct from, say, astrophysics or cosmology, where the interactions are already happening at the large scales in space, and we're just being observationists to them. So we're taking pictures and then we're inferring what happens. Here, we're actually creating the conditions on Earth by shooting in high-energy beams of protons, electrons, nuclei, and hopefully other particles in the future to see all possible interactions that can come out of this blob. And so that brings us to the plot where I actually this time did manage to add some bigger labels here. So this is all possible interactions, and this is my second favorite plot. And so that blob that I showed on the previous slide, it's a description of when you shoot in 2 particles, what are all possible interactions that can come out. And I said that we're trying to study those interactions. And so along this axis, reminder, is interesting processes that can come out. So like, for example, this column here, which you can't see at all, is the Higgs boson production. And then this is probability to make that. And you see it spans from 10 to the 11 all the way down to 10 to the minus 2. And actually, it goes further than that up and down. So 13 orders of magnitude. And you have different colors that indicate theory predictions versus experimental results. And you see basically everything is on top of each other. And so this is a very famous plot, which is showing just the sheer accuracy over a huge range of predictions, huge orders of magnitude for our theory, roughly 100 years of experimental results culminating in this. And I put a note down here because something that I wish I had said last time is that actually this result is from the LHC, but other experiments are consistent too. So we're not the only one doing experiments. Plenty of other people are doing experiments all across the world. And so far, the standard model is consistent with all of them. And then I flashed this plot that in this time I didn't actually manage to make the axes much better. And this is the year of operation at the LHC along the x-axis. This is billions of collisions along this green curve here. And it goes from 10 to the 3, so 1,000 billion collisions, all the way up to billions of collisions. And we're doing this many collisions so that we can sample this probability distribution. So you want to probe the rarest possible interactions. So you need tons and tons of collisions. And when you generate tons and tons of collisions, you then generate tons and tons of data. And so this is that purple curve from before, which is in gigabytes of data. And then this is the line that I showed before where it's total amount of data on the internet. And it's kind of crazy that you see this crossing point between them. So the reminders that I wanted to say is that we're trying to understand the very basic interactions between matter. We're trying to study them in all possible interactions. In doing that, we've gone down this experimental path where we ended up with particle collisions. We do billions and billions and billions of them. In doing that, we get huge amounts of data. And later on, we'll talk about how we actually analyze that data. And so then the point of today is to try to give high-level qualitative impressions for why we're doing this. And so what I left off of last time was that we have experimental and theoretical indications that our theory is incomplete. The way that I said this before was if you look at this plot, basically at each time slice here, whether that's talking about the scales of today or all the way up to the scales of the early universe, we have questions that we don't know about each time slice. Questions like, what is the nature of dark matter? Why is gravity so much different scale than the standard model scales? Why do we say a baryon asymmetry? And so what I want to do today is go through 7 questions that I think are some of the most important questions in physics. I'm going to give you some feeling for what the experimental evidence is or the theoretical evidence for it is. I'm going to point out which ones we think we might be able to see particles at the LHC for. And then we're going to end with some connections for what the LHC has delivered so far, which will lead us into the next lecture. So I'll pause for a second. I want to do a better job at pausing and asking if there's any questions from last time or if there's any questions on these refresher slides, just so we're all on the same page. Yeah?
So what was the unit of peak luminosity on your graph?
The unit of peak, this is 10 to the 34 centimeter minus 2.
Is that the number of particles per unit area?
Yeah, it's the instantaneous luminosity. So it's roughly the probability per second, the peak probability per second at the LHC. And then how we go from this axis to these axes is you take this, you integrate it over time. So for us, we integrate it over, 15 years of running. That gives you total integrated luminosity. You then convert that to number of collisions, then convert that into data set. Okay. Any other questions?
I have a question.
Yeah.
The gluons,
Yeah.
they hold the protons together.
Mm-hmm.
Is there any way to say what their nature and how they hold these these protons together? What is this glue is made of?
Give me 5 minutes, and it will be one of the questions. It will exactly be one of the questions. Any other questions? Okay. So first, I wanted to do something which was define our goal for this section. So I'm trying to divide these lectures roughly into 3 sections each time. And this subject matter is massive. And so for this section, what I'm wanting to do is give a qualitative overview of the standard model and the free parameters that go into it. So this is going to be a very short introduction. And then define the questions, the evidence, and potential solutions. And so the first thing to start off with is the general framework for the standard model. And so maybe you've seen this mug before. This is a mug that you can get at CERN, which has the standard model equation in its shorthand form in just 4 lines. And a fun story is that this is actually my mug. This was the mug that I bought the first day I got to CERN when I was, I think, 19 or something like that. And I've brought it all over the world, and this is a picture of it just the other day on my desk here. And the thing that you should notice is in shorthand form, it looks relatively simple. Okay, there's a bunch of squiggly lines on this that probably don't make sense, but that's not important for now. And if I wrote out the entire form, okay, it would take multiple pages, but in its shorthand form, you can see some important features of it. The first thing is how you can get to this form. So the entire form is generated from symmetries. So there are 2 types of symmetries primarily in this. There are global symmetries, which is, for example, the laws of physics should behave identically at this point in space as another point in space. This provides a strong constraint on the possible equations that we can write down. And then there's internal symmetries, like, for example, if you take one type of quark, these quarks come in different generations, and so maybe there are properties that you want to be able to have that you want the particles to be identical when you start exchanging these properties. So when you include both of these symmetries, you get an entire form, a highly constrained form for what the type of equations you can write down are. And inside of here, you have interactions and you have mass terms. So without going into detail, I wanted to say a few words about what each of these terms are. So these first 2 terms are interactions between either the force carriers. So this top line is interactions like, for example, between gluons. Then this second line here is interactions between mass particles, like, for example, quarks, and how they're mediated by force carriers, like, for example, gluons. And then these other 3 terms down here are interactions with the Higgs field. So this line here is how the matter particles acquire mass. So this is an interaction between, like, for example, the electron and the Higgs field. And so this is, if you've heard the thing of the Higgs is what gives everything particles, people are referring exactly to this line here. And then the next line is roughly what gives the force carriers mass. So, like, for example, the W and the Z boson. And then the last term here is the Higgs interacting with itself. And so all that I really want to say here is that this entire form is constrained by symmetries. And as my old advisor Yenji used to tell me, if you come up with a new symmetry, that's basically you coming up with a Nobel Prize winning equation. And so symmetries is really what dominates this. And you can really read off from here the different interactions and how particles acquire mass. And so throughout this section, I'm putting articles at the top that if you look at the slides later on, you can click on them for the ones that I thought were really good that go into these in more detail.
What L? What is it? Is it the force?
L is what we call a Lagrangian, and it's what we call a Lagrangian, which is just an equation that is describing the interactions between particles. So
what is this dimension, that entity?
This is a mass to the 4th. It's a weird dimension term because you have to integrate this over space-time. So you're integrating it over 4-dimensional. So, for example,
what do you get in this case? The dimension of L is, what is it?
If you integrated this over 4 dimensions, then you would get interactions that happen every day. So you would get interactions.
Interaction is the force.
Yeah. So, like, for example, the force that you're talking about is described in these 2 terms. So these 2 terms, like, for example, electromagnetism is described in a term like the first one. And what this is here is writing all 3 different forces and the Higgs inside of a single equation. It looks like. Right. And so then I said that what we do is we tune. This is cool. Yeah, so then we tune the theory by experiment, and I said there's at least 26 free parameters. I say there's at least because there's 26 that we know about currently, and as we'll talk about, there's problems that we don't understand yet, and maybe this could add more. And those 26 break down roughly like this. And so there are 3 couplings for the forces. So there's the electromagnetic force, there's the weak force, and there's the strong force. And from each of those, you have a strength for how strong that force is when you interact 2 particles. And so that gives you 3. And then you have 14 particle masses. And so this diagram here is a different representation of the standard model. So you have 6 from the quarks, so the up, charm, top, down, strange, and bottom. Then you have 6 from the leptons, the tau, the muon, the electron, and then the 3 neutrinos, where we don't actually know the ordering of these neutrino masses. And then you have 1 from either the W or the Z boson. It turns out that you only need 1 of them. And then we have 1 from the Higgs boson. So that gives you 14 mass terms. And then we have 2 other classes of more peculiar terms that I'm not going to go into too much. The first one is called mixing angles. And what that is saying is that actually what we're talking about here when we say particles, these particles can mix between each other, meaning that if you observe something, it may actually be a composition of 2 different types of ones. And we describe that mixing in terms of angles. And then we have so-called CP violating terms, and this I'll talk a little bit more about later. And so all of these terms, we measure an experiment, and after we measure an experiment, we then go to, if I'm an experimentalist, I then go to my theory colleagues or my phenomenologist colleagues, and then they input these parameters into their model, and then they generate large-scale simulations. And a good point about this is that the theory is extremely tightly woven. And so another person that I like listening to a lot is someone named Monica, and she's one of the physics coordinators of our experiment. And she really harps on that the theory, the measurements, they are so deeply entangled that changing one, even a little bit, can have a huge implication for the predictions of the theory. And so this is kind of a cute example of that I like to think about. And so this is the so-called stability of the vacuum, or the fate of the universe. And what you're looking at here is along one axis here, this is the mass of the Higgs boson. And along the other axis here, this is the mass of the heaviest quark, the top quark. And it's this mass here because the mass comes from the interactions with the Higgs field. So the most massive particle is the most important. And then these different bands here are the vacuum, so just empty space-time, how stable is it? And down here is saying that that vacuum is extremely stable. The way to have this in your brain, roughly, is if you have a hill, are you a ball at the top of the hill that if someone comes along and pushes it, it rolls down? Or are you a ball at the bottom of the hill where if you push it, you stay there? Or are you some intermediate region where maybe you tip over, maybe you don't tip over? And so this region down here is stability, meaning if someone comes along, you're this ball at the bottom of the hill, you're not really gonna decay. This region here is instability, which means you're all the way at the top, you're flying over. And then this region here is metastability, which means if someone comes along with a strong enough kick, then you're going to decay. And if you look at where we're predicting, where our measurements are, we're right in this metastability region. But we're in this metastability region, meaning that if we go to high enough energy scales or wait long enough, the empty space that occupies the universe will probably decay to something else, which can have implications like instead of an expanding universe, maybe all of a sudden it condenses and crunches. But the interesting thing to me here is how close we are here to this region here, and actually to this region here. So these scales here, if this is 172, up here is 176. And then down here is 170. So just a very small change in the actual experimentally measured value can push you into different regions here. And so this is an example of where you have hints that maybe this is a problem. Maybe you don't like that the universe can decay, and so maybe you think that there could be new physics there. And so I'm going to pause a second and say if there's any questions.
The universe is stable?
Metastable, so far as we know.
It is a metastable,
Yeah.
the universe.
Yeah.
But it's possible if something happened, it becomes stable.
Yeah. The good thing to know is that when we say it's metastable, we say that our predictions currently say it's metastable. But our predictions could be wrong. They could be wrong in that if we find a new particle that answers some of the questions I talk about, this whole plot could change.
And what does stable universe mean?
Yeah.
Does it mean expanding universe or not?
It has relation to expanding universe. So like if you go into a meta-unstable state or a completely unstable state, you might get something like instead of expanding, we all of a sudden contract. Or when I say all of a sudden, I mean over billions and billions of years.
So expanding universe is the stable? Or is
Related.
A condition?
No, but related. It's not, you can be in a stable state and be expanding. You can have gone to an unstable state and then start to contract, but they're not exactly equal. There's some relation between them. Yeah.
Quick one. Do all astronomers, 100%, agree with the hyperinflation period?
Right. I'm forgetting to do something, which is Mary reminded me to actually repeat the question. So the question was, do all astronomers agree with the hyperinflation period? All cosmological evidence is that the universe is expanding. For sure it's expanding. And then the question is the rate of expansion accelerating? And that, the measurements so far are pretty conclusive that it is. And so that'll be, that it is.
Oh, it is.
That it is. And so that'll be one of the questions we talk about. Right. So now what I want to do is go into 7 questions that are open problems in physics. And I'm going to give a blanket warning, which probably you're already feeling, is that this is a conversation that is high level and is very confusing. And so we're going to attempt to make it less confusing, and we're going to have one slide on each of them. We're going to pose it as a question, and then we're going to think about what that question implies. So the first question is, why is there a large gap between the gravitational and the weak scales? So this is a problem that is known as the hierarchy problem. And so this plot here is by another person I like listening to a lot. Her name is Lisa Randall. And what you have here is the energy scale. So this right here is the electron mass. Then you have the proton mass. And then you have, for example, near the Higgs mass. And then all the way up here, 16 orders of magnitude, is the scale at which gravity becomes important. So 16 orders of magnitude difference between the scales that we're probing with the standard model and the scales where, for example, general relativity become really important. And if you convert that into length scales, you can say something like this is all the way down to, say, 10 to the minus 8 centimeters, and then 10 to the minus 33 centimeters. And so this question, you could think about it in multiple ways. One way to think about it is, well, if this is the number I measure, it's just a number. Maybe I don't read too much into it. Maybe somehow there's a coincidence and we get this large gap here. This would be, there's no real problems with it. Maybe the universe just conspires to give you this big gap. Another read of it is that maybe we should expect some new physics in this region here, because why would there not be? And that read of it, then you can go and look at our theory, and what you end up seeing is that when you compute the mass of the Higgs boson, that you have very important features that depend on this scale here. And so this is a generic motivation for new particles. So to say again, the question here is a question of why is one number so much bigger than another number? And that those numbers being so different is extremely confusing, and we don't have anything in our theories to actually generate those numbers, and we would like something that bridges the gap between them. And also, I'm not going to keep asking questions, but on any of these, just raise your hand and just shoot in. Yeah.
Does this mean gravity is weaker than other forces?
Yeah. Yeah. So gravity, it falls off like 1 over r squared, and the gravitational constant extremely small, and so you have to go to extremely small scales for the gravitational force to be of the same, to be of an important scale. Yeah. Yeah.
I guess this is probably, can you hear me?
Yeah.
This is probably a stupid question. She's not here to answer for herself. But I know that Lisa is interested in string theory.
Uh-huh.
So I'm curious as to why she was concerned about gravity versus a weak force and the difference there in terms of
Yeah.
force.
Yeah. So I will blanket statement and say I'm not an expert on string theory, so take everything with maybe a grain of salt. But in string theory, you can get dynamically ways to generate this gap. You can get predictions from string theory that actually solve a problem, this problem. If I put on my experimentalist hat, the question I would ask is, how do I test it in a lab? And we currently don't have any way to do that. So I don't personally read into it all that much right now.
Okay.
Yeah. Yeah. This is not to say that it couldn't be right. I would love for it to be right, but I just don't know how to test it. Yeah. Okay, so the second question is the so-called generation hierarchy. And what this is a question of why are there 3 generations of particles with different masses? Now, what do I mean by generations? Well, I told you that there's 6 quarks, 6 leptons, and they were arranged in these rows and columns. And actually what this is we call this the first generation, this the second generation, this the third generation, and they're identical copies of each other, except more massive. So for example, this is roughly 2.2 MeV. Then you get a scaling of something like 1,000 to 2,000 to go to here, and then you get a scaling of an extra 100 to go to there. So there's copies of the particles that we experimentally measure. We have seen all these particles, and we have constraints that in some cases there's exactly 3. And we have no idea why they come in copies like this. I think if I was to dive deeper into that, it's maybe, to me at least, not so surprising that you have copies. I mean, for example, you have different energy states in the atom. The atoms can be excited to different energy states. But why is there exactly 3? And why the exact mass scales? That to me, I find extremely confusing. And maybe there's something dynamically that sets them. Yeah?
Those white are all fermions and the color are all bosons.
Yeah. Yeah. The question was just double checking that the white are all fermions and these are all bosons, meaning these are all spin 1/2 particles and these are all spin 1, which is just another set of quantum numbers, a way to describe the particles. So this general ordering, extremely confusing. There are theories that can somehow generate these, but we don't know how that happens. So the third one is coming to your question. The technical thing that people talk about is called QCD confinement. So QCD is the full term is quantum chromodynamics, and it's the theory of the strong interactions. And then confinement is why do we see protons with quarks and gluons bound inside of them? And so the question is, what is the detailed description of the physics of parton confinement? And so what that means is we have a rough description of why this happens. This is because the interaction of the strong force at lower energies gets stronger. And so what you see in this plot here is along the x-axis an energy scale. So this is the lowest energy or the longest scales. This is the highest energy or the smallest scales. And you see the curve goes up, and this curve going up is a measure of the strength of the interaction, which means that if you're starting to talk about things on the scale of the proton, the force of the strong interaction goes up, and as that happens, you just have to bind inside of protons, or else it's more energetically favorable to produce new particles just out of the vacuum. Yeah.
We know of electrical force.
Mm-hmm.
We know gravity force.
Mm-hmm.
This strong force.
Yeah.
What is it?
This strong force is so there's 4 fundamental forces. We know gravity, electromagnetism, the weak force, which mediates like nuclear decay, and then we know of the strong force. And the strong force, similar to electromagnetic force, with some important differences like this. And it's just another one of the fundamental forces. So it's, I guess, the 4th one or the 3rd one.
For the electrical force
Yeah.
to exist, you need positive charge,
Mm-hmm.
negative charge.
Yeah.
Gravity force, you need masses.
Mm-hmm.
What do you need to generate
Yeah.
the strong force?
Yeah. So there's a coupling, but maybe the direct answer is the exact analogy to the electrical charge. There's a charge for this. The charge that we call it is the color charge. Yeah. Yeah. So there's 3 different. So whereas in electromagnetism there's 1, in this there's 3 different types of charges.
It is the interaction between the colors.
Yeah. Exactly.
I thought that the confinement was explained by Wilczek and Rose as asymptotic freedom was a screening effect.
Yeah.
That this was because the color is carried by the glue.
Yeah. So the question was, I thought that this question was actually answered by someone before. This question was kind of answered, and so this plot is actually taken from an article that talks about Frank Wilczek's and the predictions. What I think I mean more specifically is their predictions give you a high-level reason for why you should expect things to be confined. But as the confinement happens, we don't know exactly how it proceeds. So like if we had 2 corks, we started to separate them and we ask how they get confined, that exact process as it's happening, we don't have a good way to describe it. We have an overall, yeah. I mean, the way that people will describe it now is you have 2 corks that are attached by a spring. It goes far enough, the spring breaks. I don't know. That doesn't make me feel super good. Yeah. It gives you 2 more quarks. It's somehow weird. Springs now. I went from quantum field theory to talking about springs. I don't know. It feels weird. Yeah.
And electrical forces,
Yeah.
we can measure the force
Yeah.
in terms of the electric charge and
Yeah.
Coulomb's
Yeah. Coulomb's law.
constant.
Yeah.
Okay. In gravity force, we have G.
Yeah.
The universal gravitational constant.
Yeah.
Okay. How do we measure the strong force?
The analogy of G and the electrical force, the coupling of electromagnetism, is exactly this, which I should have made much bigger, is exactly this number here. How we measure it is we do
Is
fits.
there a universal constant?
It's a universal constant.
There is
Yeah.
What is it? The
It's
universal- a key.
the name of it, we call it alpha S, alpha sub S.
Alpha sub S.
Yeah.
That's what it is.
Yeah, that's exactly what it is. And the important thing to see here is how this constant changes at different energy scales. This is the exact opposite behavior of what you have in electromagnetism.
So the constant changes.
Yeah.
And the mass.
Depending on the energy scale or the length at which you're looking at it. So the really important thing to say is this behavior here, which is well known and well explained, is completely opposite of electromagnetism. And that being opposite is exactly why you end up getting protons and confined quarks and gluons. Yeah. So the 4th problem, I will blanket stay and say, to me, this is the most hard to think about problem. This is the so-called strong CP problem. And so this is a picture from a Forbes article where, if I remember right, the name of it was something like the biggest problem that nobody talks about. And the question here is, why is there CP violation in the weak interactions, but not in the strong interactions? So first, what is CP violation? What this cartoon is roughly trying to show is you have a particle. First, you have C, which is charge symmetry. So you take that particle and you flip its charge, so you go to its antiparticle. And then P is parity. And what that in this cartoon is you take the particle and you look at it in a mirror. So you say, how does the particle interactions in a mirror look like? Now, roughly, this is saying, do things that happen with your right hand behave the same with things that happen with your left hand? Yeah.
How do you implement charge conjugation with three colors?
So the question is, how do you implement charge conjugation with three colors? Here, we're talking about electric charge.
Oh, that's only two.
Yeah, plus and minus. Yeah, yeah, yeah. And okay, so what we're talking about in essence is how does a particle's antiparticle, which in theory is an exact clone, just with the opposite charge, behave when you then look at it in a mirror. And in the weak interactions, which is where you have, like, for example, the W and the Z bosons, which mediate, for example, beta decay, you actually see that if you look in a mirror, what happens is different. So the right-handed behavior is different than the left-handed behavior. This is extremely peculiar, but not ruled out in the standard model, and we do see it. So it's not actually weird that we see it. I mean, okay, it feels weird because it's uncomfortable to think about, but from the view of the theory, it's completely allowed. Now, in the strong interactions, so like the force that we were just talking about, it's very similar, and you would expect to see something similar orders of magnitude. And actually, the constraints on it now are 10 to the minus 10 what we predict in the standard model. So it's extremely, extremely small, and it's so small that it's just ridiculously confusing. We have no way to explain it, and the implications of it are really broad. For a thing I'll talk about on a later slide, for example, like the matter-antimatter asymmetry, this type of force, CP violation, is an extremely important ingredient to actually get matter-antimatter asymmetry. And so why these numbers are really small, extremely confusing. And the ideas for it is that maybe there is some mechanism that can generate this small of a number. So this is the so-called axion, which is an extremely light particle, and maybe it could set these couplings to a small number. So that's the fourth question. The fifth question is matter-antimatter asymmetry. And yeah.
I hate to do this, but
Please.
can you connect chilarity with, I'm a layperson. I'm struggling between chilarity
Yeah.
and symmetry. Is that when the violation from symmetry does occur?
Yeah.
Does chilarity seem to be
Yeah.
involved? Yes?
Yeah. So chirality, you're talking about handedness.
Yeah.
And then the symmetry that we're talking about, violation, is exactly that one chirality, so right-handed, doesn't behave the same as the other one. It's exactly that. Yeah. Okay, so back from the weird land of CP violation, back to something that maybe is slightly more understandable, the matter-antimatter asymmetry. And so the question here is, why do we observe more matter than antimatter? And the actual technical question is, why do we observe more baryons than antibaryons, where a baryon is like, for example, the proton? And in very loose terms, the evidence that we have for that is this so-called baryon to photon ratio. And so it's, if you look out in space, very early on in the universe, if you had the same number of particles and antiparticles, and if they annihilate with each other, you produce photons. And so you have a giant amount of photons. But then if all of a sudden there's some process where antimatter starts getting annihilated more than matter, you'll have a slight excess of matter. And that will then translate into elements being formed. So like, for example, lithium, helium, or deuterium. The rate at which we see these when we look out into space is exactly tied to how many protons were around to actually build these things. And so we can measure this with either cosmic telescopes or satellites, and we can compare it with our predictions either from the cosmic microwave background or from the Big Bang theory. And so we have extremely strong evidence that you do have an asymmetry. The asymmetry, just to give you a feeling what we're actually talking about, the scale that we're talking about, this number is 10 to the minus 10, and this number is 10 to the minus 9. So we're talking about an asymmetry on an extremely small scale that then gets amplified when we evolve across the universe into what we see now, where if you look around, I mean, we're all made out of matter and not antimatter. So it's an extremely small asymmetry. And the conditions for this were laid out by a really great physicist named Sakharov. And he laid out 3 conditions for how you can actually generate an asymmetry like this. The first one is you need some process that actually differentiates between matter and antimatter. So you need to produce more matter than antimatter. Then you need CP violation. You need CP violation because if you have that process that can produce more matter than antimatter, but then you don't have CP violation, that same process can just be run in reverse. And so then you start sloshing back and forth. And then you need, for the universe temperature to drop fast enough where that asymmetry gets frozen. So you produce an asymmetry, it sticks, it freezes, and then we see it at our time scales here. What is the point in me mentioning this is that this question really ties together maybe 3, if not 4, of the other major outstanding questions. Yeah. Please.
So do they think the antimatter that was produced is somewhere else in the universe, or clumped, or it was just neutralized, destroyed?
Yeah. So the question is, do we think that the antimatter is clumped somewhere, or do we think that it was actually destroyed? And I actually see Ben here, who I work with at Fermilab, and we actually just talked about this. The current idea is that it's not clumped somewhere, like, for example, dark matter clumps in places, that it actually, there was annihilations that happened in the early universe where the antimatter was annihilated. It was actually annihilated. And in it being annihilated, you produce photons. So they annihilate, and then you produce light. And so that light is this. That's why we measure the ratio of the part of the matter to the photons. Yeah. So it's not that there's some clump sitting out somewhere where all the antimatter is sitting. It's really that it's gone. It's gone, and we don't know why. Yeah.
Every time there is a decay or there is a collision where the particle is broken down, it emits a lot of photons, which means that these photons were there, okay, to be emitted afterward.
Yeah.
Do these photons play any role in the internal forces? Do they have a role in keeping the protons together? Do they have any role of gluing things? Okay. So that's the question.
Right. So let me repeat the question, see if I know actually what your question is. The photons that are produced in the early universe, when you have particle decays or you have antimatter matter colliding, you produce photons. Do those photons play a role in keeping nuclei together, or do they play a role in other things, generally? That roughly the question?
Yeah.
The answer is yes. They don't play a role, a large role in keeping nuclei bound together.
They don't.
They don't. That's mostly the strong that's the strong interaction.
They don't.
Mm.
And the gluons are different from the photons.
Yeah. What they do play a large role in is as the photons they produced early on in the universe, and then they travel great distances, and then that's what we actually measure.
So why are they there?
What do you mean? Why are they? You mean?
Photons, why are they inside as a part of the particles before they were broken there? I mean,
I think maybe correct me. I think you may have in your mind that the photons are inside of the particles before they annihilate. That's not what we're talking about here.
they are inside the protons. They are inside the electrons.
Right. That's not what we're talking about here.
Photons.
Yeah. We're talking about in particles colliding and annihilating, photons being produced. So not inside of them.
Yes.
Yeah.
Well, if they are produced, so they were already part of the particles before they collided.
No. That's a good way to look at that.
They are produced from where? I mean,
Yeah.
is it because we know that in semiconductors, when electron moves from the conduction band to the valence band,
Yeah.
it emits an electron,
Yeah.
and it can be seen when there is
Right.
a collision.
Right. This is
So the photons are real that are emitted.
right.
In this case, for an electron to release a photon, the photon has to be part of the electron before, isn't it?
Right. So the analogy to superconductors, for example, where you have electrons moving from valence bands, and then as they move, they slow down, so they so-called Bremsstrahlung, where they emit a photon. That's different than what we're talking about here. That also can happen. The idea that the photons were already part of the electron, I think more what you're saying is that around the electrons, there's an electric field. And as the electrons accelerate or decelerate, you know from E&M that they emit photons. That's different than what we're talking about here. We're talking about particles coming in, annihilating with each other, and in that process, producing photons.
I know what you're talking
Okay.
about. Okay. My question is
Yeah.
really restricted to these particles that
Yeah.
emit the photons.
Yeah.
Okay, that means the photons were part of the particles. Okay.
No, I think the point here,
Okay.
And in this case, is there any role for the photons when they are part of the particle?
Right.
Are they playing any role inside that particle?
I think with how you're thinking about it, the technical answer is yes, because you're talking about particles that are interacting via electrodynamics. I think it's not exactly the way that you're talking about it is not exactly right. For this, we're really talking about particles isolated from photons, where the photons are not interacting. But if you pushed me to the edge of, well, do they play any role? There is some role that happens, but then you have to go much more into the theory of it. Yeah.
you think the confusion here is that when two protons come together
Yeah.
and produce photons, the photons were not in the proton, it's from the energy that was produced.
Yeah.
Photons were created.
Yeah. So that's how I am interpreting this. If you went further and you said, well, isn't there some chance, because there's electrically charged things inside the proton, that there are photons in there also? I mean, the answer is yes, because there's quarks in there that are electrically charged. and there'll be photons flying around. So there's some impact,
Yeah, I can see.
but from the level that we're talking about, it's not there. Yeah. So why don't we talk about more after? And so the sixth question is dark matter. So the actual question here is, what is dark matter? Is it a new particle? And we have evidence from dark matter, which is that it interacts gravitationally, but that it doesn't emit light. That doesn't emit light is an important point here, meaning that so far, our telescopes here on Earth that are observing things in the universe, we're doing that by measuring photons that hit us, so light. And if dark matter was interacting a lot with electromagnetism, you might expect a lot of photons to be coming at you that you wouldn't have otherwise had. We don't see that. What we do see is that they add extra clumps of mass. And so this is a very famous plot, which I think was the result that won the Nobel Prize for it. And this is a measure, so-called galactic rotation curves. And so this is what it's trying to show is a galaxy, and how far from the center of the galaxy are you, and how fast are particles around the galaxy moving. And this dashed line here is the prediction from effectively classical mechanics for if you have most of the mass in the center of the galaxy and then it starts dropping off, the velocity should start dropping off because it goes like 1 over r squared, and so you have less mass on the outside, so it starts to drop off because the rotational speed. But what we actually observe is this line here, where you have that it actually goes up. And we have that from 2 different sets of measurements over a long scale from the center of the galaxy. And the interpretation of this is that there is a mass density around the edges of the galaxy that we can't actually observe from them emitting light. And so we infer them from seeing the rotational speed. And the current estimates for how much this dark matter occupies the total amount of energy density in the universe is roughly 25%. And so what this pie chart is showing is this sliver right here, which is best estimate is around 4.6%, call it 5%, is everything we've been talking about so far. So all the matter that exists, all of us, everything, roughly 5%. Then dark matter, roughly 25%. And then what we'll talk about in the next slide, dark energy, roughly 70%. So we are talking about mostly 5% of what we know exists in the universe, and we would love to know what this is. Yeah.
This is mass, like the dark energy. If this circle here is mass, that means the dark energy, this is the mass of the dark energy, the blue.
No.
So the dark matter, 24% of the mass of the universe or the energy of the universe?
The energy mass density. So the
Energy.
like E equals mc squared plus p squared, the total energy mass density, roughly the total energy density. So this I guess maybe the more direct way to say this, this plot makes no comment about what the mass of a dark matter particle could be.
4.6% is a mass.
This is energy.
Energy too.
Energy dash mass, combination of them.
Energy dash mass.
Yeah.
Okay. This is the now one other question.
Yeah.
You said the dark matter around the galaxy. That's what I heard from you say.
Yeah.
Around the galaxy.
Yeah, like a halo.
Is it inside the galaxy, in the center of the galaxy, or on the outside of the galaxy?
On the, it's along everywhere, but primarily along the outside, like a halo.
Halo outside.
Yeah.
So it exists outside the galaxy.
When you say outside, I mean on the edge, not outside, like It's not like the galaxy's here and it's all the way over there. It's like it's part of the galaxy, but until these measurements,
Shell,
yeah,
it is a shell around the galaxy.
yeah. But the surprising thing, just to emphasize, is we had no idea it was there. The galaxy ended earlier from measurements before this. We thought that the energy density along the edges of the galaxy dropped off, and we had no idea it was there. And only from measuring the speeds at which particles are moving along the edges did we infer that there's actually more mass there than we thought.
But there's dark energy throughout the galaxy. Right here, there's dark energy.
Yeah, so just disentangle dark energy and dark matter in your brain. The name is inconvenient, just dark because they don't interact with light.
If the dark matter exists like a shell around the galaxy, and its mass energy is so huge compared to the
Yeah.
galaxy itself, that means its density has to be really huge.
Yeah, it's huge.
Huge.
It's huge.
It is transparent.
Yeah. So far as we know. People do all sorts of cool experiments. People do all sorts of cool experiments to see how transparent it is, how much it interacts with the electromagnetic force. Maybe my favorite experiment, which is kind of funny, is called light shining through a wall, where you shoot light at a wall and then you see if it interacts with dark matter and then see if it comes out the other side. You just put a wall there. So there's all sorts of cool experiments like that, but so far as we know, transparent. Yeah. This we know is roughly the correct breakdown from measurements from NASA and something called WMAP. So this is where you have satellites up in space that measure the photons coming from different contributions. We do measurements, and then we have a theory prediction, and we do fits. So we have data points, and then we fit, and these numbers are actually the results of fits. Yeah. Maybe we should talk more after.
Just one
Yeah.
question here about hurricane and tornadoes.
Okay.
They have spiral arms
Yeah.
like the galaxies.
Okay.
So should we say, because they have similar spiral arms,
Yeah.
that there is a shell around
No.
that the hurricane that is there, and
You're saying, are there dark hurricanes around the middle hurricane? Yeah.
Sometimes you really have to watch things to
Mhm.
learn about other things.
Sure.
Okay, and you really have to observe here and
Yeah.
observe there.
Right.
Okay, and they try. You see, there must be something. There's similarity. There's been a lot between hurricanes and between galaxies.
The rotational speed, yes. This problem is different.
Well, the spiral arm.
Yeah.
Why do how they originated? Why there is a spiral arm? Okay.
Okay. Sure. Okay. Afterwards, let's talk more about it. Yeah.
Question. Do you have any reason to believe that there's reactions between dark matter and dark energy? The graph shows it as certain
Uh,
or is there a reaction?
so far that we know, there's not. Disentangle those ideas in your brain of dark energy and dark matter. Completely disentangle them. The names are weird, unfortunate coincidences, in my opinion. So far that we know, there's not. And maybe that brings to the seventh question, which is maybe the last question. I had maybe 5 more slides after this, so if people need to start going, no problem. But the last question is, what is dark energy? And so the actual experimental evidence for this, from the Big Bang, you expect pressure-driven moving outwards. So you have a lot of energy in a small space, and then it explodes, and you know that it's going to start expanding. Okay, so you have an expansion. And then you can ask the rate of that expansion. Is it constant? Is it decreasing? Is it increasing? The only way it could be increasing is if you had an additional pressure that came in and gave it a kick, so that it started to increase. And so this is a different form of the evolution of the universe. And roughly what we see is in the beginning, we have this inflationary period. So we have the universe expanding. And then sometime over here, so far as we know, when the contribution from dark energy started to grow, the rate of expansion started to accelerate. And so we can see this by making predictions for where, for example, we see different stars, different supernovae in the universe, and where we think we should see them. And they're at different positions. And that exactly maps back to an accelerated rate of expansion. And so the question here is this dark energy a constant? Is it the same pressure throughout all time, just at later times it became more important? Or is it actually evolving with time? And so there are other questions, but just to summarize, so these are the 7 questions. And then roughly the first one, so the hierarchy, so why is gravity and the weak scales at such different scales? Why are there generations of particles? Why in the weak force do you have CP violation, but in the strong force you don't? Why is there matter-antimatter asymmetry? What is dark matter? Is the universe stable or unstable? There are theories that resolve all of these, and all of them make predictions that we may have new physics, new particles at experiments like the LHC. So at exactly where we're probing right now. And so then I have maybe 3 more slides, which is the 2 main outcomes of the LHC that I can say very succinctly. So I'll pause here and I'll ask 2 questions. 1, if there's any more questions, and then 2, if everybody needs to run, then I can postpone this to next time, or I can keep going and talk for maybe another 10 more minutes. Okay. So there are 2 main outcomes so far. The first main outcome is the discovery of the Higgs boson. So before the LHC turned on, we had predictions for the mass that the Higgs would be at, but we had never actually produced it in the lab. If you ask people who were on the collider before the LHC, they may say, maybe, but probably not. And how we did that was we did it in 2 different modes. The mode that I'm showing here is a Higgs boson comes in, which is represented as this dashed line, and 2 photons come out. And then you get a plot that is the so-called mass distribution. So this is the mass. This is the number of events. And all that we're talking about is this little bump right here. So this little bump right here at 125 times the proton mass is a resonance. Just like, for example, if you have a noisy vat, and then all of a sudden it hits a resonant frequency, and it oscillates at a resonant frequency, that manifests from quantum field theories as a particle at a particular mass. And so this plot is the exact evidence that we see the Higgs. And then the second main outcome is nothing else so far. And this, I just put, I couldn't really think of what to even put here. So what I did was I took from the experiment I work on all of the different measurements. Now it looks like, I don't know, there's 30 here, but what you should see is that there's 30 here, and then all of these different subscripts are different individual measurements, and then individual measurements upon submeasurements, and then this axis here is the mass scale, and what we've probed so far is up to roughly 15 times the Higgs mass, which is around 2,000 times the mass of the proton. And this nothing else is extremely surprising. To me, this is, if you looked at predictions, the conversation before the LHC, it was that we were going to turn on within 6 months, a year, we were going to find the Higgs boson. And then within 3 years, we were going to find a whole bunch of other particles. And all of those 7 problems, 4 of them we were going to bang out. We were going to know tons and tons of more things. And we found nothing else. And what does that mean? That means that the very theoretical ideas that led to these predictions, a lot of them probably have massive holes. And this has really upset a huge deal in the field. And this will be the starting point for next time. So like I said, next time we're going to appreciate a bit more what finding nothing else even means. And then we're going to translate those limits and the physics questions that we had into motivation for new measurements. And then those new measurements will lead us into the coming lectures where we start talking about AI more and more. And so that's the plan. So next Saturday we'll talk about that. And then I did want to leave off on one more thing, which Ed actually pointed out and wanted me to bring up, was that, I don't know if you saw, the Physics Nobel Prize was announced a few days ago. And it was given for foundational discoveries and inventions that enable machine learning with artificial neural networks. So you're giving a Nobel Prize for using physics to start the area of AI. And then I wanted to actually ask the question and maybe get a poll if people would like me to spend maybe 5 or 10 minutes next time talking about this and some details why this was given. Yes? Okay. Okay. So next time I'll start off with a bit of that. So that's all I had. Thank you. I'm here for questions. And